Hello, welcome to my talk on Newton's invention of calculus. In here, I will talk about what is exactly the Newton's calculus. Principally, calculus is an evolving thing, and as early as in the ancient Greece, Archimedes had used the method very similar to the calculus to obtain the volume of a sphere. But why we say today Newton is one of the core inventors of calculus with Leibniz. This talk would make an explanation on this. In this talk, I will introduce what is the Newton's calculus. A brief introduction will be made on this. And then I will introduce 3 Newton's quadrature rules which allow calculus for more complicated and practical applications. The proof of the quadrature rule 1, we will see how Newton solved the complicated calculus problem. And then the application of Newton's binomial series, which simplifies the complicated problem for calculus, and the summary of Newton's calculus on what problem Newton solved or what breakthroughs Newton had made for calculus. Isaac Newton was one of the greatest mathematicians in the history, and one of his greatest contributions was the core invention of calculus. But what is exactly the Newton's calculus? Here I would like to make a brief introduction on that. Newton's calculus is also called as the method of fractions, based on the reference 1 here. For Newton's calculus, as the modern calculus, we have 2 different ways. The direct method of fraction, it is equivalent to the differentiation of modern calculus. For instance, for the known length of the space, to find the velocity of the motion for mechanical problems, or the non-flowing quantities, Newton used the word fluent to determine the fractions, and the inverse method of fractions, which is equivalent to the modern calculus, the integration. For instance, if the velocity of the motion is known, to find the length of the space, or if the fractions are known, and find the flowing quantities, the fluents. In Newton's calculus, Newton's terminology and notation for calculus, fractions equivalent to derivative, Newton used x dot y dot. This is still used in modern calculus. Here, x dot is the differentiation of x with regard to a variable t. Fluents are the variables as x, y, and etc. Moment, the differentials. In Newton's notation, it would be given as y dot o, and the modern calculus would be given y dot dx. And the inverse method of fractions, the integration. In Newton's notation, it is given in a rectangular box, and now the integration is given as this, the Leibniz notation. Principally, Newton's calculus is a combination of his important development in mathematics, this including the binomial series, the inverting algorithm, the quadrature rules. These are the topic in this talk, and we can see the obvious calculus element in these rules. In the next few slides, the quadrature rules will be introduced. In this slide, quadrature rule number 1, the quadrature of a simple curve. If y is given as a simple function of x, it's the curve AD, where a is a constant and m and n are positive integers. Then the area of the region A, B, D is given as this expression, based on the reference here. In modern calculus, this rule is very simple. However, in Newton's time, this development is very important. Next, we will see 2 examples. The first example is we have a function y equaling to ax squared. This is an element power function of x. We can easily calculate y with the increment delta y because of the x is increased by delta x. So we can calculate the increment as this. So delta y would be given as this. And then we can calculate the derivative or the change of y with regard to x. So it is given as the limit of the ratio delta y over delta x when delta x is close to 0. So we have the expression for the derivative as this and this, because delta x would be close to 0, so the second term can be dropped. Obviously, such elementary expression with the power function of positive integers must have been available in Newton's time. And one of the Newton's contribution was to extend the calculus for the more complicated function, that is, the power function of fractions. If we look at the expression here, we can see obviously Newton has extended the theory to the power function of fractions. Here, m and n can be any integer, but m is not equal to minus n. For instance, suppose we have a function equaling to ax square root. This is a special example of the expression y equal to ax power of m divided by n with m 1 and n 2. How its derivative and the integers can be calculated. Newton gave the answer for this in this quadrature rule. Here we must note it. Before Newton, there was no method for expanding the function as ax plus delta x square root. And it was Newton who made the Black's rules in this, based on his binomial series. Such an advancement allows calculus for much wider applications for practical problems. From the modern calculus, we can easily see the quadrature rule number 1 is correct. Quadrature rule number 2, the quadrature of curves composed of its simple ones. That is, if the value of y is made up of several such terms, simple curves, the area should be made up of the area which result from every one of the terms. This rule means if we have a function as y equaling to y1 plus y2 plus y3, etc., here y1, y2, and y3 being the simple curves as we seen in the previous rule. Thus, in modern expression, this rule is given as the integral of y is the integral of y1 plus the integral of y2 and plus the integral of y3, and so on. This can be easily proved using a graphical way. For example, if we have the LDO for a function y1, see the hatched LDO. So the LDO is calculated as this integral. And we have the second LDO given as this, the integral of y2 given by this. Here, we make the difference of these two LDO. So it can be easily seen graphically how we can do this. If we use the LDO of this, take away as this, so we have the hatched LDO as this. And this LDO can be calculated using this expression, the integration here. Therefore, we can prove the summation rule of quadrature given as this. It should be noted here whether the rule is for summation or for difference. The principle is exactly the same. This is the proof of the quadrature rule number 2. The quadrature rule of number 3 is for the quadrature of all other curves. If the value of y or any of its terms be more complicated, and then it must be reduced into more simple terms, and use the rule number 1 and number 2, we can obtain the LDO of the complicated curve. Based on the Newton's binomial series, this is the only expansion Newton used. We have seen this before, and here each of A, B, C, D represent the previous term. And now we may use Taylor series instead. However, it was not available to Newton. Taylor series was developed after calculus. Take an example, P equaling 1 and Q equaling to minus x squared, M equaling 2 minus 1 and N equaling to 2. And based on the Newton's binomial series, we can expand the binomial function as this into the binomial series this. So from this binomial series, we can see each term of the binomial series is the simple curve of the power function, and the area corresponding to each term can be easily calculated. So, based on the Newton's quadrature rules, we can obtain the area of the complicated function, as well as the derivative of the complicated function. This is the purpose Newton developed his quadrature rules for calculus. In the next few slides, the proof of the quadrature rule 1 will be made, and we will see how Newton solved the complicated problems. It is interesting to see Newton used an unusual way to prove the quadrature rule. He actually started from the known area of a curve, or the quadrature z given by this, and then he derived the function for the curve. Here, suppose the area of A, B, D is taken as z equaling to zx. See the hatched area. Now he supposed a point beta on the x-axis with a small distance. Newton used O to represent the small distance beta to b. Hence, A beta would have a length x plus O, and Z x plus O would be the area A beta delta. Newton then introduced a rectangle B beta HK of a height of V equaling to BK and beta H. And the area of the rectangle is the same as the area B beta delta D beneath the curve in this small region. As such, the area of B beta delta D would be simply calculated as O times V. In Newton's proof of this quadrature rule, he assumed the area under the curve is known given as Zx expressed as this, and his purpose was to find the instantaneous rate of change of z, as y is the derivative of z with regard to x. That is, to find the function of the curve y. It should be noted, even in Newton's time, it is well known that the derivative and the integral calculations would be an inverse calculation. This means if we find one, for example the derivative or the integral, then we can easily obtain the other, simply use the inverse calculation. Following the Newton's derivation, we can take C as the expression as this and P equaling m plus n. So Zx can be expressed as C x power of P divided by n if we see this expression here. So we can obtain the equation as this. So dx power of n equaling to C power of n times x power of P. And if we consider the increment of the area due to the increment in x, so we have the expression as this. And as we have seen before, the area of z for x plus O, it should be expressed as z plus OV. So we have the expression as this. Next, Newton applied his binomial series for the binomial function, this and this part on both sides. So we have the expansion for the binomial series here, the left-hand side given as this, and this for the right-hand side. So consider the original expression here, so we can take these two terms away. Thus, we can divide in the equation with the small increment O, so the equation would be given as this. Here, in this term there's no O, and this term there's no O, and this term is 1 O, and this term. You can see here O here and O here. So if we take the limit of the equation when O is close to 0, in such a case V would be equivalent to Y. Hence we have the expression reduced to this, and we can obtain Y given as this from this equation. So we replace back of the z function C and P, so we have the expression for Y as this, and this, and this, and we can see this part would become as this, and here the power minus 1 is divided by x, and here minus 1 would become this divided by x power of m plus n divided by n. Now we can cancel all this same value for the numerator and the denominator. So here n would be cancelled out, and the m plus n would be cancelled out, and this term would be cancelled out. Therefore, we have the expression for y given as this a divided by x. Denominator would be 1 divided by x power of m plus n divided by n. This will give an expression for y simple as this. Hence, we finish the proof of the quadrature rule number 1. From the expression of the area on the curve zx here, we can derive curve would be given as this. Infinitesimal calculus, or more simply, calculus, is basically an evolving thing. As early as 250 BC, Archimedes employed similar technologies to obtain the area of a circle and the volume of the sphere. And many other scholars have contributed to the calculus development. This both before and after Newton and Leibniz. Then a question would be why we say it is Newton and Leibniz who co-invent calculus. The main reason for this is both Newton and Leibniz had made the breakthroughs which brought the calculus to much wider practical applications. In Newton's case, his contributions include Newton's binomial series for the generalized binomial function, which is a huge advancement in analytic mathematics. The quadrature rules, especially the rule 1 for the derivative and the integral of fraction power functions. This is another big breakthrough to bring the calculus for the practical applications. The basic rules for decomposing the integral terms to make the application of the calculus possible for the complicated functions. The inverting algorithm of infinite series. Some fantastic examples of the calculus applications, such as the infinite series for sine and cosine functions. The earliest applications of calculus to the dynamics and motions, creating a new era for physics and mechanics. And I think without Newton's contribution, calculus would be limited to some applications, and we will not have the fantastic mathematical tools such as the Taylor series.